In our last couple of videos, we're going to focus on some of the applications of infinite series, and especially Taylor series, to problems in math and science. And in this video, we'll look at pi. Now, the number pi comes about when studying a whole bunch of different problems in geometry, but the most basic example is when you think about the circumference of a circle. So we have a circle, the circumference, we know is pi times the diameter of the circle. So if we measure the distance across, call that d, there is some ratio between that diameter and the circumference that is constant for all circles. And if you look throughout human history, you'll find lots of examples where people tried to estimate what that ratio was. For example, in the Bible, if you look at designs for, say, the temple, you'll find that the circumference of the pillars was estimated to be around 3 times the diameter of the pillars. Okay, so they used an estimate of pi is approximately equal to 3 when trying to do certain engineering feats like building a temple. And different cultures throughout history have had different estimates. And so let me show you just a few of those. Okay, so here in this table on the left, we have a few different estimates that have been used for pi. So 3, you notice that is actually off by about 4.5% from the true value of pi, but it's not a terrible approximation. Another fraction that sometimes people have used in history is 22/7, which is a decimal is about 3.1428571, and that's actually 0.04% off from the true value of pi. So for most practical purposes, unless your measurements are incredibly precise, you're not actually going to notice that much of a difference between 22/7 and pi. So in ancient China and ancient India, they also had different estimates of pi that they used. One fraction that's even more accurate is 377/120, and so that's off by 0.002%. And then if you use 355/113, you can get even closer, and so the percentage there is quite small. So it's a very, very good estimate. Now, each of those fractions works well as an approximation, but what happens if you want to be able to estimate pi to, well, any degree of accuracy? How do you actually generate an approximation that's as accurate as you could possibly want? Well, there are a variety of ways of doing this, but one of the methods that you can take is based on infinite series. And so let's take a look at how we would do that. All right, so first things first is let's look at a triangle with a 45-degree angle. And 45 degrees in radians is pi/4. And if you have a 45, 45, 90 triangle, then that means that the ratio of the opposite and adjacent sides is 1. So we can say that the tangent of pi/4 is equal to 1. Or another way of writing that equation would be that pi/4 is equal to the arctangent of 1. And therefore pi is equal to 4 times the arctangent of 1. Now, we don't have a great way to calculate the arctangent of 1 if we don't have pi, right? But we do have an infinite series to represent the arctangent of x. The arctangent of x was given by, and we calculated this earlier, the sum from n equals 0 to infinity of -1 to the n times x to the 2n plus 1 all over 2n plus 1, which if you plug in different values of x, you'll get x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on down the line. Okay? So we have an infinite series to calculate the arctangent of x, and that series is convergent for x values between -1 and 1. And what that means is, if we plug in x equals 1, then we should get a series that converges to pi. So pi should be approximately equal to 4 times 1 minus 1 cubed over 3 plus 1 to the 5th over 5 minus 1 to the 7th over 7. And notice those numerators are all just 1, so I'll stop writing them. Plus 1/9 minus 1/11 plus 1/13, and so on. And so as we add more and more fractions, we will see that this series converges to pi. And in fact, if we wanted to estimate pi to arbitrary accuracy, we could use what we know about alternate series to determine exactly how many terms are required. So suppose for a second we want to estimate pi to within 0.01. Well, how would we do that? Well, we just need to look for the next term in the alternating series that is below 0.01. And so we would look for a term where 1 over 2n plus 1 is equal to, is less than 0.01. And so we can rearrange that equation. This is just 1 over 100. So we could write that as 100 is less than 2n plus 1. So 99 is less than 2n. So n is greater than 99 over 2. And so if we go further than 99 over 2 terms in our series, then we should be able to estimate pi to within 0.01. So that's going to require just around 50 different fractions that we'll add. So by the way we're counting is using the definition of n in the series above. So that means we need 50 terms from that series to get there. Okay? So pi should be something like 4 times 1 minus 1/3 plus 1/5, all the way on out to 1 over 2 times 50 plus 1, and that should be within 0.01. Okay, so using alternating series, we now know how to estimate pi to whatever accuracy we could possibly want. And just to illustrate that graphically, so here's our arctangent function, and here I've plotted, this is actually 4 arctangent of x plotted in purple, and in blue I've overlaid the Taylor series with n terms in the partial sum, and you can see that with 100 terms it is quite close to the arctangent function, and the estimate with 100 terms is 3.15149, so we're off by just a little bit. We want 3.14159, and so if we added a few more terms, maybe go out to 1,000, it actually takes a minute to calculate here, but you'll see that you do indeed get a better estimate. Okay, so one application of infinite series is they can allow us to calculate the values of transcendental numbers like pi, or also e, to as high a degree of accuracy as we could possibly want. All right, in this case, with 1,000 terms, we've got 3.14259, so not terrible, but you will notice that this actually converges to pi relatively slowly. You need to add up a lot of fractions to get a good estimate, and so there are some clever tricks that you can apply to take this series and turn it into a faster converging series that are actually used in practice, but the principles are the same.